Mainly.
So we are very happy to have Ayush with us. Ayush did his master's here in CMU. He was in the MSR program. Okay, Ayush has been in our lab for a very long time, even 1 year before starting the MSR program. He has worked very hard so far. He's going to discuss all his published works today and his future, current and future plans. He's now a PhD student here in CMU. Yeah, we're very excited to see what he has to say. We're going to listen to him. We're going to ask questions, right?
Yeah.
Ask questions, and then at the end we can ask more questions. And how long is your talk? 30 to 40?
Yeah, 30 to 40.
Yeah, we want to keep it
Yeah.
Okay. Wonderful. The topic is language, vision, and action. There's nothing less.
Yeah, we are quick to solve AGI here.
What's left?
Just 1 more minute and then we can start.
Very nice. So you can see I usually there are things, brought cookies and drinks, which none of my previous students have done. This without me telling script. Okay, so please go ahead and right?
Yeah.
Is it from which unique cookies or?
No, so some of them are from India. There are some special Indian fruit biscuit, and some of them are from Chipotle. Actually, Chongwei helped a lot. No, it's very clear. So I put the Indian fruit biscuit first so that people eat that, and then Chipotle.
But me, Ayush is one of the very few students that worked super hard from far away. So he was the whole summer in India to be closer to family. But despite the enormous time zone difference, it's as if he's all the time available all the time. Yeah, so he can work from anywhere.
Yeah, I think we can probably start. Hi, everyone. Thank you so much for being here, and thank you, Katrina, for the wonderful introduction. Today, I'll be discussing language conditioned object detection and manipulation. If these slides progress. Okay, it does. Let's imagine a future where we have robots that can actually help us in our day-to-day life tasks. Right now, I think we struggle with them to get some mundane tasks to happen for our robot projects and so on. But let's imagine that at some point, these robots actually become useful to us. These robots would need to interact with wide varieties of objects and would need to do wide varieties of tasks in our diverse home environments or office environments and so on. So one fundamental question that we need to answer before we move on to solving, let's say, robotics is object detection. And a deeper question is, for example, what is an object? Prior methods sidestep this question by first defining a vocabulary of objects that they care about, and then they would go on, collect a data set and label all the objects that are mentioned here, that are in the fixed vocabulary. Then they'll take an input image, take a neural network, and would spit out all the objects in this image, which are present in this fixed vocabulary. And I think this already looks very great. But what happens when an object is not there in our vocabulary? So for example, this robot was not detected by this detector simply because the robot was not in our vocabulary. Well, maybe many of you would say that, okay, we'll just add this robot in our fixed vocabulary and we are done. But what about this sentence? Like if I say to my robot, peel the orange in front of you, then in the previous setup, we would need to have this orange in front of you in our vocabulary, because I do not want this orange to be detected, neither this orange, but specifically this orange. So instead of having a fixed vocabulary of objects that you need to define a priori, what you could do is feed the language instruction directly to the model as the input. So in this setup, if the sentence is cut the orange in front of you, you detect the orange which is in front of you. And now in this setup, if you have this question, what is an object? Well, an object is whatever that is mentioned in the sentence or is relevant to our task. And this setup of conditioning language initially early in the model is also very useful for robotics, because for like a very easy way to communicate to our robots is through a language instruction. And if you supply the language instruction and they can follow it, then I think our lives would become pretty easy, maybe. So in this talk, I'm going to discuss our work on language, on object detection, which is conditioned on language for both 2D and 3D scenes. And I'll also discuss an application of such an object detector for language conditioned robot manipulation and show that relying on this object detection from a language conditioned detector and building on top of it by generating goals and so on, we could easily do a lot of very hard and diverse tasks. Let's first talk about the language conditioned object detection. So as I described earlier, the setup is that we are given an image or maybe a 3D scene, and we have a language instruction like cat on top of the chair. And the task is to detect the cat and the chair, that is the mentioned objects that we have. A common paradigm for these methods is given an image. We first fire a pre-trained object detector to get a bunch of proposals, Then what we would do is that we take these proposals that our detector gave us, and then we just train an object selector network whose job is to just select the bounding boxes out of these all proposals. So from all these proposals, the object selector network said that these two boxes belong to the objects that are mentioned here. For example, this green box is for the cat and the orange box is for the chair. Now, this is a very popular paradigm and has worked really well. But let's think about a scenario where our object detector itself fails. So for example, if we didn't detect the cat in the first place, then the object selector network can't really do anything because it does not have any box to select from. And this problem is not only in 2D, but in 3D as well. In 3D, the object detectors are even less robust compared to the 2D detectors that we have. And most benchmarks, that's why they just supply you the ground truth box as input to your model. So they don't say that fire an object detector. They just say that, okay, take these ground truth boxes and just select the box that is mentioned in the sentence, which is obviously a major assumption. I think humans do things differently than this detect then score pipeline. Let's see an example. So we have this image, a very beautiful image, I think, and we need to, many objects might just pop out of it. But maybe this clock is probably not the first object that we notice, or maybe we even didn't notice this clock at all. Our state-of-the-art object detectors also missed this clock, and so this detect and then score pipeline is going to fail. But if I had said earlier that, okay, you have to detect the clock on top of the shelf, I think we would be able to detect this clock because this top-down guidance from this language instruction would help us detect this object. So the main point here is that if you have a language instruction, then you should utilize the hints that are given in the language instruction to detect the objects, rather than first doing an object detection without knowing the task and then trying to select one box out of it. This is what we design, and this is our architecture. So we take the input scene and the language instruction. We fire a pre-trained object detector to get some initial proposals. Then we encode each of these modalities through their respective encoders. So for the scene, if it is a 2D image, you could encode it with resonant 50. If it is a 3D scene, maybe you could use pointnet++. For language, you could encode it by a BERT model. And for the object detections, we simply use some small MLPs to encode these objects. Then these modalities attend to each other to contextualize themselves with the cues that each of these modalities have. Then we instantiate some object slot vectors. These object slot vectors are simply like the anchor boxes that we know in object detection literature. And these anchor boxes, let's say, attend with each other, cross-attend to the modalities that have contextualized already, and then they would decode bounding boxes. So here, this green query decided to decode the plant, the orange query decided to decode the end table, and all the rest of the queries, for example, this purple query would match to saying that, okay, I'm not an object and I'm not mentioned here. Let's look at some of the key properties of this architecture. One key property, I think, is that we are utilizing the pre-trained object detector here to get some initial proposals. So instead of just starting from the input scene and the language instruction, we are also using the hints that our pretty awesome object detectors can already give us. At the same time, unlike previous methods, we are not bottlenecked by the object detector. So even if the object detector fails, we are still attending to the input visual scene, and we can still decode the bounding boxes. We can also refine the bounding boxes that are already predicted by the pre-trained detector. The other thing that we do is that we unify the object detection and language grounding. So for object detection, like I described, people used to have a fixed vocabulary. So instead of predicting a distribution of outputs over this fixed vocabulary, what you could just do is feed this fixed vocabulary input as a text sentence into the model. So we form a sentence something like couch, person, and chair. We feed this to our model, and then the queries would latch onto the couches and the chair. And since person is not there in the scene, so no query is decoded for the person here. This specific idea of unifying object detection and grounding has become very commonplace now. This paper, GLIP, came out, I think, 2 months after our submission, and has the same idea and shows that if you unify the detection and grounding, you can benefit both of the tasks simply because you are able to use more data. Nowadays, in all major vision language models, we see this pattern of unification of detection and grounding. For example, in GLIP V2, XDecoder, and grounding dyno. Now I'll move on to our results. So we compare against two baselines here. One is the previous state-of-the-art 3D model that were there, which basically follows this detection then score pipeline. The other baseline that we have is MDeter 3D. MDeter is state-of-the-art 2D detection model, and we basically made a 3D version out of it. And we find that our model outperforms both the baselines by a considerable margin. If you look at the ablations, I think this is one of the most important ablations where we are removing the visual tokens, and that leads to a decrease in 10.2%. So basically what I'm doing here is that my queries are only attending to the object proposals and the language instruction, much like what previous methods do. And this leads to a huge drop in performance. So the main point here is that it's important to attend to the visual tokens early rather than first doing detection and then doing scoring. We also find that removing the box stream, which was giving up the bottom-up proposals, leads to a decrease in performance by 1.1%. Also, incorporating these annotations by unifying detection and grounding helps our performance by 4.2%. This model works on both 2D and 3D with minimal changes in the architecture. There were some conjectures in the previous literature that maybe these 2D grounding methods cannot really work for 3D grounding. And this is one data point that proves otherwise. This is our results on the 2D benchmark. We compare against 3 popular benchmarks, RefCoco, RefCoco Plus, and Flickr 30K. We achieve comparable performance to MDeter, but we train much faster because we have architectural improvements, such as using deformable attention instead of self-attention. If we use self-attention, we couldn't train this model in our lab. Please check out our project page for more details about this project and more visualizations. Now that we have discussed how to do language conditioned object detection, let's look at the problem of actually doing manipulation or instruction following if we have a language input as instruction. So the task setup is that we have some input scene and a language instruction, and we need to basically output actions that satisfy this language instruction. One very popular class of methods is language to action. These methods basically take as input the original scene configuration and the language input and feed it to a neural network to output the action directly. Now, let's pause for a moment and think about the case when we have a very complex instruction. For example, let's say we have to make a breakfast. Now, this kind of a sentence has a lot of subgoals that need to be executed sequentially to achieve the task. And if this policy is asked to do this complex instruction, then it does not really work. We'll also show in our results that if the instruction is very complex, these language to action models do not work. The other important part about these sub-goals is that they are hierarchical. So some concepts might be something like, I'm thinking about making this breakfast. What should be my ingredients for making this breakfast? The other could be as low level as picking up the knife and how I'm closing my fingers underneath the knife. So there is a huge hierarchy of the goals that we have. And one popular way to deal with this very complex instruction nowadays is using language goals. So this is powered by the LLM revolution. And there are several works in robotics that are trying to use LLMs to do complex tasks. Some of the representative ones are inner monologue, SayCan, code as policies from our CMU itself, and it also won the ICRA Best Paper Award, and palming. The basic idea behind these models is that you have some input image and you have a language instruction. You pass it through some vision API to get a scene description out of it. So it tells you that, okay, these are the objects that are there in the scene. And this is how these objects are related. For example, red block is inside blue bowl and so on. Once you have the scene description and the language sentence, you pass it to some large language model. It does its magic and give you a simpler sentence, something like move yellow block to the red bowl. Now, once you have this simple instruction, then a language to action model that I described earlier could work and spit out the actions. So the key part here is that this LLM is going to break down the task into some clear language subgoals. Now, in this setup, the problem usually occurs when so in some of these models, what happens is that you can skip using Vision API, and you can directly supply the object models to the language instruction if you have, let's say, a large visual language model instead of a large LLM. But the idea is still the same. The output space is still in the language space. Now, the problem with these kinds of models is that when the language itself is very hard, like language becomes hard to describe your goals. And one such case occurs when you have to deal with multiple constraints jointly. So if we see this example, we have put the strawberry to the right of the apple, and we want to put the strawberry to the front of the green bowl as well. So we have to satisfy these two constraints jointly. And now our LLM basically knows that the low-level execution policy is kind of dumb and can only execute one action. So the best thing it could probably do is to ask it to do sequentially to sequentially satisfy these constraints. So it first asks put the strawberry to the right of the apple. It actually does that. And then it says put the strawberry in front of the green bowl, and the language to action policy succeeds. But the problem is that here it violated the earlier constraints. So this is basically a problem which is in the language space. We cannot really say two constraints jointly in a simpler fashion. While if we have some visual way of saying that, okay, you just have to put the strawberry right here, let's say, then it would work. There are other cases when the language becomes a problem in specifying the goals. So for example, this is an Indian art called Rangoli, which is pretty complex. And I think I would be very surprised if somebody could describe everything that is there intricately through language instructions. So there has been another revolution that is going on. The other revolution is text conditioned scene editing. So here the sub-goal space is the visual scene. So the idea is that you have some language instructions and you have an input scene, and these models would give you a new output scene that you need to achieve. So for example, you have this input image, you have some language instruction. It gives you that, okay, this is the scene configuration that you need to achieve. But the problem is that our execution policy would need to do a lot of processing, do inverse modeling to figure out what are the actions that I need to take to go from my input image to the output image. So this goal image is not really that helpful. So what we do instead is that we design our goal space in terms of actionable visual goals. What I specifically mean by that is let's see this example actually. So we have this input scene, and our task is put the red ring above the yellow cylinder and right of the blue bowl, yellow bowl. We first output the bounding boxes for the scene. So this is the space that we would operate in. We would operate on the space of bounding boxes instead of the original images. Then our goal generation model would somehow give us a visual goal in terms of bounding box that, okay, this is the location that you need to put the red ring. And finally, we have some goal condition execution policy that would spit out the action. So this is much simpler now because this goal condition policy knows that I only have to care about picking up the red ring from that location and placing it at this predicted location. It does not really have to do anything intelligent. Let's look at this pipeline in slightly more detail. So we have some language instruction. We have a language parser that spits out a bunch of instructions that the robot needs to follow. Usually, these instructions are, for example, detection. So we have to detect red ring, yellow cylinder, and yellow ball. And then some of them are for generating the actual goal. So let's first do some detection. We would use the detector that I described in our earlier project. And this detector would find the yellow cylinder, it would find the yellow ball, it would find the red ring. Once we have the detected objects, then we would do goal generation. Our goal generation model predicted the goal that we wanted to achieve. And then we would do some local goal condition execution policy. So what happens really here is that these transporter networks, which is what I'm calling the goal condition policy, just takes the crop of the image around, like crop of the object that our detector predicted. So took a crop around that, and all it needs to do is to predict from where I can pick up this object from here. So it needs to just learn how to manipulate the objects, but nothing else. Similarly, for generating the place location, it would take the goal that our generative model predicted and would say that, okay, maybe here is where I want to place my place the object. And this is a suction gripper, so that's why I'm showing the circular thing. It would suck up here and would place the object here. So these transporter networks then pick up the object where they predicted and would place the object, and that would complete our pipeline. Let's look at our goal generation in a bit more detail. So the goal generation model that we use is energy-based model. And a very brief primer of the energy-based model is that energy-based models are trying to model the distribution of the data like most generative models do. The thing is that, the generative model takes as a concept as input. So it takes the concept square as input. And the energy of the configuration which satisfies this concept is low, and the energy otherwise is high. So we train this model by trying to maximize the data likelihood of our data. And what we simply do is that we push the energy of our positive sample down and bring the energy of our negative sample up. Here, notice that I'm saying hallucination. What I really mean is that we just start from some input random configuration, and we would take some gradient steps along the direction of decreasing energy. And this configuration that we get, the updated configuration that we get, becomes the negative sample that we have. Specifically for our model, what happens is that we have this input configuration and the language instruction. Our parser says that, okay, you have to use left EBM. We would parameterize our input as bounding boxes, and the bounding boxes is represented by the two corners of the bounding boxes itself. This EBM would predict an energy for this configuration that we have right now, given that it should satisfy the left concept. So the apple should be left of the orange. So we expect currently that the energy would be pretty high. Then we would take some Langevin dynamics steps, which is basically some gradient update steps, to get to a new configuration with new updated xmin, ymin, xmax, ymax. And then what we do is we push the energy of this generated sample up, and we bring down the energy of the positive sample down. We have these positive samples because we have these demonstrations that, okay, placing apple to the left of the orange means that this is the right configuration. And obviously the generated configuration is wrong. The hope is that once we train this model, then given an input configuration, which is again the bounding boxes, we could just add the energies of individual concepts. So in training, we only train we train an EBM for left concept, we train an EBM for right concepts, and so on. And then at test time, we could just add the energies of each of them. And this energy would be basically a joint distribution over the whole sentence that we have. So this is the input configuration. Our EBMs would take some steps to get to a new configuration. And this is our final observation. This is our final observation. Okay, now let's look at some benchmarks on how we want to test this. So there is a clipboard benchmark, which has a lot of tasks, something like put the brown blocks in a blue bowl, put the red hexagon in the hexagon hole. But most of these tasks are caring about the inside relationship. So we add other spatial relationships too, like right, left, above, below, and also some shapes like circles, lines, and so on. One thing that humans are very good at and is very important for development of for humans is that they are very good at compositions. I could learn 4 or 5 simple tasks, and then I could just compositionalize them and do a very complex task. So this is the setup we want to test, where we train our models on the simple tasks, and at test time we do complex tasks. So one such benchmark that we designed for this is composition one step. In composition one step, the instruction is pretty complex and involves a lot of relationships, but the main point is that you have to move only one object to satisfy all the constraints. That's why it's called composition one step. Well, maybe why not move all the objects? So we have composition group, where we have still a very complex language instruction, and we have to actually move a lot of the objects to satisfy this language instruction. Let's talk about the results. So first of all, we compare within distribution. So we start simple and we say that, okay, what happens when we train on these simple concepts like left, right, behind, and so on, and the clipboard benchmark that we have, and what's the performance we get compared to state-of-the-art language to action baseline, which is clipboard. We find that our model outperforms clipboard in mostly all the tasks. Yes. Then we test on compositions. In this setup, we have a baseline of clipboard zero shot, which is basically a language to action model just trained on simple concepts, and at test time asked to do a very complex instruction. We also fine-tune clipboard, which is shown in purple, and it still does not improve a lot, which basically adds weight to my point earlier that for language to action models, if the instruction is very complex, it might be very hard for it to actually learn something useful. We have an LLM planner baseline, which is basically trying to plan in the language space. And the best it's probably able to do is sequential execution. And then our model is SRAM, and we are evaluating it zero shot. And we find that we are able to we are able to do much better compared to all of these methods in these compositional tasks. We also find that our model is robust to perceptual variations. So in red, we have scene attributes. Then we change the colors, we change the background, and we change the object classes. And our model does not drop performance by a lot. Why is that? Well, this is because we are using an object detector that is trained on a large amount of data. So these detectors generalize and help us. We are working over the abstraction of bounding boxes. And so bounding boxes are invariant to perceptual variations. And finally, like I described, these transporter networks are very local manipulations. So they work over a crop of the object. And that's why they can also generalize. The implication of this generalization is that we can train our model in simulation. And at test time, we could just evaluate in the real world without doing any domain randomization or collecting real world data and so on. Let's look at one example. So the task is to rearrange all small objects in a circle inside the plate. We'll detect the small objects, we'll detect the plate, and then our goal generation would generate this goal configuration that satisfies that these objects should be arranged in a circle, and they should also be inside each plate. And finally, our robot does this task. Very good. So in this talk, we basically discussed 2 things. We discussed how we can make our detectors open vocabulary by conditioning on language early, and how we can unify this detection and grounding setup so that we have one model which can do detection, which can do grounding, and it can also consume all kinds of data that we have. And this model works both on 2D and 3D. In the next project, we showed that we could build on top of these object detectors. We could use these object detectors. And then we mainly try to learn how to generate a goal. And then these low-level execution policy can follow these goals pretty easily and can compositionalize as well, thanks to our generative models. Going forward, now I basically, when I did this projects, there are some things that were kind of not satisfactory. So for example, one thing that I find dissatisfactory is we are using a 2D based object detector here, while in our setup, we had access to 3 RGBD cameras. And we know that if we have multiple images and we have access to depth, then our perception system improves. I think 2 weeks back, RI also took us to NREC to show around the robots, which were pretty cool. And all of them had access to multiple RGBD cameras. But why, if the perception is better with multiple RGBD cameras, we are still using this 2D input? Well, the main reason behind this is that the 3D based detectors do not generalize, simply because the amount of data that we have in 3D is very small. And in 2D, we have so much amount of data that we could really generalize. So one thing I'm interested is unifying the 2D, 3D perception systems more. So for example, I described Beauty Eater, where we were saying that, okay, this architecture works pretty well if in both 2D and 3D scenes without much architectural changes. But one important thing that I realized is that the input representation is also very important for this unification. So we were using point clouds, and as an implication of using point clouds, we had to rely on something like confined to encode these features. If we change the point cloud to post RGBD images, let's say, and we let's say process our RGB images through ResNet 50 or like strong 2D based detection systems, then this part of the encoder is also shared between 2D and 3D, and the 3D models can utilize all the pre-training and so on that is there in the 2D community. And the only thing probably that depth would give us is positional encodings when we are doing this attention. And since we have multiple views, we would want to fuse features across these views. So the 3D could help us know that, okay, these 3 points are close together, even if they are in different images, and then we can fuse features across them. But the point is that most of the parameters are shared, and you can feed it one image, you can feed it multiple RGB images, you can feed multiple RGBD images. So you could train with all 2D and 3D data, and at test time as well, you could supply it either 2D or 3D data, whichever is available on your robot. The other thing that I realized is that the output space is also very important. So for example, in our previous project, we were predicting bounding boxes. So for 2D, you have a 2D bounding box. For 3D, you have a 3D bounding box. But if we shift to segmentation, let's say, then in both 2D and 3D, all we have to do is pixel labeling. So there is also no difference in the output space, and the output parameterization is also similar. So what I want to do with this project is basically unify 2D and 3D and get to a state where we have better models that could really generalize, and we could use our 3D input. The other thing I described in, let's say, SRAM is that we were able to do some tasks, some complex tasks, like rearrange small objects in a circle inside the plate. But these objects are still pretty toyish. The setting is also pretty toyish. So I want to build towards following complex demonstrations. For example, see this demonstration. She's making a very beautiful salad. And even though I'm very bad at drawings and so on, I could probably follow her and make the salad myself as well. The problem in this setup is basically that our perception system becomes a bottleneck because we do not do fine-grained perception. We do not have a 3D understanding of the world. So in my previous proposal, let's say, we were trying to use the scale of 2D data to help 3D learning. I think what would be important to go to this kind of setup is if we have a 3D prior of the world by, let's say, utilizing whatever small amount of 3D data that we have. And so we could infer 2D much better compared to what we do right now by simply processing the 2D input. I think this is probably it. Thank you so much for listening to me. This is my amazing committee. Thank you so much for all your feedback and help. And I think this work wouldn't be possible without my friends and lab members. Some of them are here as well. and my family who supported me throughout this project, throughout this master's. With this, I'm happy to take questions.
Okay, thank you.
Nikos? Sorry, go ahead.
Sure. First of all, I have to say, I really like the work. I think it's very interesting, and it's really in advance compared to even a few years ago. There's so much that's going on right now.
Thank you so much.
And it's a good talk. So most of my questions have to do with you helping me understand
Mhm.
some of the limitations
Mhm.
of these approaches
Mhm.
better than I currently do.
Mhm.
So for example, I think one of your very first slides, don't go back to it, asked us, what is an object anyway? And
Yeah.
you had some examples. And you pointed out that language actually helps you resolve that question, because sort of any concrete noun phrase is an object.
Yeah.
Is the attitude you took. But then you said, well, my system is based on this predefined object detector, which caused me a little bit of cognitive dissonance.
Mhm.
Because I'm thinking, for example, I could say this strawberry is an object.
Mhm.
I could say this banana is an object.
Mhm.
I could say this bowl is an object.
Mhm.
Or I could say this fruit salad
Mhm.
is a thing.
Mhm.
And that fruit salad is actually those strawberries and bananas inside the
Mhm.
bowl. So what I'm getting at is just this issue that obviously there are different levels of aggregation of the parts
Mhm.
that we sometimes refer to as an object,
Mhm.
like a fruit would be a simple example.
Mhm.
So help me understand how you deal with these kind of varying levels of aggregation of
Mhm.
objects,
Mhm.
given that we do have some predefined objects.
Yeah, I think if I understand correctly, the question is that we are using an object detector, which is obviously fixed vocabulary, and still we want to detect more objects. We want to detect maybe other parts of things like salads. We want to detect the individual fruits as well. How do we do that given we have this object detection, which might be a bottleneck? So I think the answer basically is that this object detection thing is just an addition over the attention to the visual features. And in the training part, let's say in the training, we would have sentences like fruit, the orange in the salad, let's say, and then we would have labels for orange and we would have labels for salad. So at training time as well, it is trained to detect objects even when they are not in the predefined vocabulary. So this predefined vocabulary is just there to help us a bit. Let's say, okay, detect some big objects. I also expect it to fail a lot on the small objects, and we do not care about its failures. What we care about is, okay, these are the objects. Maybe this might be helpful for you to solve the task, and the model figures out that how to actually solve this task.
So are you saying that you're counting on your object detector to find both the strawberry and the banana and the fruit salad?
No. So I'm not counting at object detector or at all. It can fail on like all of them. It might not detect any of these objects, but still, since we are attending to the visual features where we have all the information that we have, and we are training in a way that we have to detect oranges, fruits, and so on, then we can detect the objects. In earlier works, the problem is that you throw away the visual scene. So there is no way you could detect something that you have already thrown away since your object detector didn't detect it. So because we are not throwing away these objects, that's why we are able to detect these objects. And the second part of the answer is, if you look at this object proposals, these object proposals are like, we take 100 object proposals, and you might see that it has an object for the chair. It also has the object for the leg of the chair and so on. So these object detectors, when they have a lot of proposals, even when they are trained on, let's say, like 1200 categories, it could still produce reasonable boxes for other objects just because they start to recognize the objectness of the objects and so on. So this is the other part of the answer. So mainly we are not relying on the object detector to give us the final bounding box, but the object detector can give us very reasonable input. So that's why we are utilizing it.
Okay, another question has to do with, maybe we could call it instructability,
Mhm.
but, what would it take for your system to be maybe extended
Mhm.
so that I could define new, words
Mhm.
with meanings?
Mhm.
So for example, I might say, looking at this
Mhm.
photograph, I want to define a new thing called a groove.
Mhm.
And what a groove is, it's one of those horizontal things that, actually is not one. It's a set of those horizontal things that go between the legs of the chair
Mhm.
that keep the legs
Mhm.
like strong, so they don't squash out when you sit in the chair. And, I can see a groove there,
Mhm.
but, I just want to say, want to instruct you
Mhm.
to define. Is that something that you can handle? Is that something that you could easily handle if you extended?
Mhm.
Help me understand.
Yeah. So the answer is yes and no, because in one of the projects, like for example, this beauty editor project that has to output the action or the objects directly, this does not really have a very good way of instructing about new concepts. But the other project that we have where we are using these generative models for defining the concepts for us, I think this is the perfect slide for it. If my animations, yeah. So here what we have is a library of energy-based models. So we have one energy-based models trained for one individual task. So let's say you define me a new task, for example, make a triangle that I've never seen before. I'll just train on this making a triangle thing and add it to my library of behaviors. Then this library of behaviors would give me the new concept of triangles. And this low level policy that has to actually execute the task does not really care about the task. It just wants to take the goal location and place the object there. So it has nothing to do with new concepts. So the new concepts can directly just be added to the library of EBMs, and you could extend it to whatever concepts you want.
So that's interesting. It makes me wonder, like, how far could you go with those kinds of definitions? I mean, kind of an example that people use is, let's define a chair as anything I can sit on, which is really not a geometric description at all, right? Help me understand.
Yeah, I think that's an excellent question. So I think our abstractions helps a lot, but it restricts us a lot too. So for example, the concept that you described, there is no way we could do it with the abstraction like boxes that we have. And actually at some point in the project, we were also discussing that, okay, we want to have this affordability and so on. And we were thinking that maybe we could rely on segmentation instead of detections, and those things can move around. But I think it's still kind of hard in this setup where we have this strong abstractions that limit what we can do with it. So I don't think this could be very easily extended to non-geometric concepts, let's say, or maybe deformable objects as well.
Yeah, I think for those kind of functional definitions, you really need other modes of reasoning, for example, about stability.
Yes.
So that makes sense. Let me pass the baton and preserve the right to come back for more questions later.
Yeah, thank you so much.
Sure, yeah. By the way, very nice talk, and I really liked some of the technical aspects of the energy response there, and joined modeling for the incorporating language in the first one. Maybe a couple of questions to first just help me better understand a couple of aspects, and then a couple higher questions. So in this one, the example that you had, put things in a circle, can you just walk me through again how the energy-based models let you get that configuration? In particular, is there a specific model that you trained which can handle this circle-like instruction, or is it something that's coming from composition of some other models that you had, and this inside a circle is a new instruction?
Yeah, I think that's a great question. So We have actually two kinds of energy-based models. One is for binary relationships, where we have to model relationship between two objects, and one is for multi-array, for example, circle, where multiple objects need to be in some configuration. So we train one EPM for circles, like training some things in the circle, and one EPM for the inside energy.
So it's not as if this is a new instruction for you, right?
Yes.
So just, I guess, maybe an open question, and it's okay if you don't have a concrete answer, but in a lot of other language-based applications, what's really evocative to me is you can give arbitrary, unseen, like, teddy bear in New York Times Square, which probably you didn't really ever see during training, and it can still reason with that. But this current approach does, in some sense, I would argue that there's no need for language, right? It's just instruction of template 1, instruction template 2. Like I could replace language by some arbitrary text as long as I'm giving you consistent data for it. So is there hope for extending this to be as compositional as like this goal prediction model or this energy-based model to be as generalizable as we see these other language-based models be? Because to me, that really is the promise of language, as opposed to only following things that you already saw the templates for.
Yeah, I think that's a great question. And probably my answer is that we could take the best generative model that we have, which is trained on a lot of data, and just replace our energy-based models with that generative model that could predict a goal. The only important detail that we need to figure out is that, like I described, if a generative model just give you a teddy bear on a sofa, it's very hard for an execution policy to actually place the teddy bear on the sofa. It has to infer that it has to place it. So we need to actually say that we have to basically link that our input scene was this, and this is our generated output, and this object moved here, this object moved there, and so on. So I think that is an interesting problem to solve as well. But other than that, you could use any generative model for predicting a goal.
Okay, I mean, you need paired data to train such a model, right?
You mean paired language image data?
Yeah, pair initial image, language, goal image data. Right?
Yes. So we have a lot of this kind of data in videos, let's say. And if let's say language, maybe if we have captions, we have language, otherwise we don't have. But all we need for learning this concept is some initial configuration and some output configuration. We do not need anything kinesthetic to like solve this task. So I think videos is a very good way to get this kind of data and learn these things.
Okay, yeah, but though in that, just to be clear, there'll not be any language.
Yeah, most probably there won't be any language there. Yeah.
And I guess, okay, so you had this very nice slide in the first project of this clock on a shelf. And I'm curious if you tested your model on that and it was detecting it for the right reason.
Oh, yeah. So actually produce this image from the model, but I have quantitative proof that it helps. So okay, but what we did basically is that we were seeing that, okay, in some particular scene we get some outputs, right? In what percentage of times our detector failed, and yet our model was able to detect the scenes, and in what percent the detections was already there in the detector and we were able to detect the scene. So we found that there are multiple such cases where the detector actually failed and we were able to predict the bounding box. Now, since and in 3D, I think it's a fair comparison because we were training the detector on ScanNet, and this joint model was also trained on ScanNet. So there are some reasons to believe, at least, that because of the language conditioning, it was able to detect these objects.
Okay, and I guess one last open-ended question more on the manipulation side, and maybe this is evoking my mental model of Abhinav, but the last project had this very clear demarcation that given image and maybe this language instruction, we'll have this goal representation, and then it's the perception system has more or less done its job, and on to you, robot people, right? And I am wondering whether you think this demarcation is a good thing if we go to complicated tasks. For instance, if you ever watch a video of how to make a French omelette, there's this step, okay, let's fold, and I can tell you how to fold, but I have no idea how to even generate goal images for that. It's more about, okay, you've seen it enough, you've tried to do it, then you can do it. But I personally would not be able to give you goal images or bounding boxes or anything for what should happen or what should an agent try to achieve as it's doing that. So towards, like, are you philosophically ascribing to this framework where there is this demarcation that input is sub goals in some form predicted and then some robotic system takes over? Or do you think you'll need to throw this away at some point if you want to do more complicated stuff?
Yeah, I think that's again an interesting, I think it's a very good question. I think I subscribe to this philosophy more, that for like the benefit of the other approach when we have these object detectors is that we have a lot of data on which we could learn good perception systems, while for robotics tasks, let's say, we have fewer amount of data and there learning the perception from scratch is kind of hard. So, and at the same time, I agree with you that for some objects, we don't have like bounding box thing, for example, deformable objects, or there might be some other scenarios where we cannot define these objects. So I think my philosophy is something like you should use an object detector, let its prediction help you whatever it can, but at the same time, you should not just rely on the object detector like we were doing in the second project. You should still keep the input as whatever it is. So in the cloth case, maybe it helps to detect the table and that helps. So yeah.
Okay, thanks.
Any other questions? Don't you have other questions?
I do actually have a follow. I like this question and made me think of a kind of related one, which is this. The way that the examples that you've given of using language are really about language for defining objects. That was the title. So
Yeah.
fair that that's what you were doing. But when I think about, say, acting in the kitchen and cooking a French omelet, part of what I use language for, if I'm teaching somebody, is not about objects, but about trajectories. But about videos instead of states with objects in them.
Yeah.
So for example, I'll say, one thing I do when I make an omelet is I scramble the eggs, I put them in the pan, I mix up the eggs, put them in the pan. And then when it starts to get a little bit cooked, I scoop my flipper under the egg, and then I lift it up just enough so that the liquid part of the egg can slip under there. Okay, so that's the use of language to describe a trajectory, not a state or even a part of a state called an object. And so if we wanted to steal all the good ideas in your system, we build a system that could handle both objects and, let's call them processes, video trajectories, so whatever you want to call them. What would we do?
I think, yeah, that's a great question. I think the title here is robot instruction following. But when we started this project, we wanted to do robot coaching, where we want to teach robots something. Here, it's more about specifying the task, and that's the only use of language. But maybe what you are describing is that language is very useful to describe that this is what I am doing, this is how I am doing things, and so on. So I don't think it really fits in this framework. But what I think is that it lets you label these concepts. For example, I'm making a circle of some things, and I'm saying I'm making a circle of some things, and this is how I made it. So I would learn that, okay, this configuration is called circle. And let's say maybe I train a generative model to say that, okay, when somebody says make a circle, I would make this configuration. So I think the language there is possibly trying to help by using the primitives that we have. So for example, you mentioned scooping. Let's say I've learned what scooping means in general, and we and my goal generation model says that, okay, you have to actually go there and scoop it up, then this is really helpful, because when we are instructing, we are trying to use the primitives that maybe we have already taught or the model has already learned, let's say maybe from some YouTube videos or something like that. So I think this form of language that you're describing for instruction following is basically trying to compositionalize the simpler concepts that the model has learned. So I think it's basically in some sense, in my biased mind, it's basically an extension of this kind of idea where you could chain the language concepts.
I guess one way we can think about this would be, there's recognition and then there's control, right? And when it comes to videos, maybe taking them both on at once is a big job. But suppose we just want to recognize. Suppose I just want to say, here are a bunch of videos, find me scoopings where the liquid went under the partially cooked egg or whatever. Could I, for example, take your architecture and replace with where you have the image coming out, replace that by instead of video, and pretty much keep the rest the same.
And
although maybe now I want a lot of verb phrases, not just that.
Yeah.
Would they kind of, what would happen if we tried to do that? Just for the recognition part. Not for the,
so if I'm understanding correctly, let's say I'm seeing a video and I'm basically saying, detect the scooping part out of it, let's say, and I have to identify these frames were responsible for detecting the scoop. Probably that's what you're thinking about. I think this can be trained, but the problem usually is that we don't really have such kind of data. What we have the data for is that somebody is instructing, maybe let's say in a video, and we do some temporal matching to say that, okay, this is at this particular time, this language word was spoken, and that's when the action, and that's when the actor actually did the task. So I think instead of language input, maybe we would need some sound kind of input or some temporally aligned language and video input. And if we have that, then I think we could train such a model, and in theory it can work. I'm not sure if it would actually work or not.
anyway, thank you. Interesting work. Plenty of future direct.
Yeah.
Thank you.
So I took away your lot, so I'm going to ask you a question. So now we like class for this to be also
Okay, let me. Hi, Zoomland. Do you guys have any? Yeah, Nikos is there. Oh, yeah, Nikos, do you want to ask some questions? Maybe I should share my screen. Yeah.
Very unlikely.
Yes, hi.
We used to sit together every day, talk a lot. So, yeah.
Can you hear me?
Nikos, fire away your question.
Can you hear me? No?
Yes, I can hear you.
We are not able to hear you.
Okay.
Can you hear anyone from the Zoom?
Nikos, still not able to hear you.
I can hear him on Zoom. Can you hear me?
Yeah, I can hear you. Yeah, Chris is also there. Yeah.
Yeah, I can hear Nikos as well, so I can relay his question. Nikos, what's your question?
Okay, let me try again now.
Yeah, now it works. Yeah.
Okay. Yeah, so, okay. Hi, Katerina.
Answer your question.
Hi, Chris. I mean, that's only 2 days ago.
First of all, I really like your talk, and it was very nice and on time, and the flow was good. And one thing that you didn't, maybe I didn't understand, maybe I missed that, is you showed some results where the manipulation model was better than the baseline clipboard on atomic concepts. And I can see why it's better on compositions or novel objects, let's say, but why on scene concepts in generalized so much better? What do you think?
Yeah, I think the question is about this slide where we have like atomic concepts and why clipboard model works better compared, like why our model works better compared to clipboard. I think it is because we are modeling the geometry and all these relations explicitly, while clipboard model has to rely on the features to directly output, let's say, what is left, what is right, and so on.
Nice. So modeling explicitly the geometry, what do you mean with that?
Yeah, so basically, we are starting from, like, we have these abstractions of object bounding boxes, and we are explicitly moving these object bounding boxes. Also, in our energy-based models, we have, like, all these objects are parameterized as relative to each other. So they know about the relationships about in the objects and so on. So that's why I think this model can better reason whether something is to the left of something, right of something, and so on.
I see. So if I borrow the term from your first part of the presentation, we would say that this method is kind of grounded bottleneck.
Yes.
Right?
Yes, you're right.
And then I wanted to ask you a question, but Subham kind of asked it. Where do you place yourself between one extreme and the other? But you picked one extreme. So I just wanted to ask then, the second extreme that you kind of rejected has two nice properties, this composability, and what Tom asked on how easy it is to add new concepts. So since you picked the other, I mean, you tend towards the other extreme. What's your opinion on those two nice properties? How could we achieve something like that using an end-to-end model, even if it's conditioned on whatever other signal you want?
Yeah, I think the question is that in the first project, we are like saying that, okay, you should have visual features as well, and you should attend to them. While in this project, we have this object detection bottleneck. So if object detector fails, then rest of the things failed. And I said that I like that earlier setup better, where we still have the object detector, but we also have the visual features to predict like the action, whatever action that we need to take. I think in that setup, one part, like I think if we change the parameterization from bounding boxes, let's say, to directly visual features, then maybe we would lose out on these properties of compositionalizing, like left, right, and so on. So I think maybe we would need to choose our abstraction based on the task. For these tasks where we have rigid objects, I think it's pretty good that you could detect these objects. And I don't think there is any hope that you could learn better perception by training your object, like training end to end here compared to an object detector if you have rigid objects, because it utilizes all that data as well as this new data. So if you have rigid objects, I would say go with the second approach and use the object detectors. But in cases like what Shubham mentioned, where we have these deformable objects, cloths, and so on, I don't think we can even do this parameterization of bounding boxes. So we don't even have the properties that we have here right now. So all we would have to do is rely on our generative models, like all like decent generative models that do not have this box bottleneck, let's say. And in that case, sure, we could just condition on the visual features and also attend to the detection that we have. So in summary, the answer is maybe it depends on your task.
So let's pick one hard task that doesn't allow you for these abstractions. Can you think of any way to achieve compositionality using an end-to-end model?
With an end-to-end model, I think probably not. Even in object detection literature, what happened is that we shifted to this end-to-end models, and there is another set of approaches which are neurosymbolic and have all these abstractions and everything going on for them. I think recently a new alternative has come up, which is trying to use, let's say, LLMs or code generation models that take a very compositional sentence, break them down into simpler ones, and then you execute them. So I think in that case, we would need to rely on such kinds of breakdown sentences. But yes, if we have to use these joint constraints, and maybe I don't think it might work, and we would have to rely on the single constraints at a time. But the good part is that in actions, usually we have more sequential actions. So maybe it would help there. It would work there.
And okay. And yes. And about teaching new concepts?
So about teaching new concepts, I think one way is probably something like analogical models that maybe some people in our lab are pursuing, where the idea is basically that if you have a new concept, you just supply that new concept and the model learns to analogically do a new task. So I think those kinds of models where we could do, let's say, retrieval and so on, those could help us add new concepts faster and better compared to our vanilla language to action or vanilla end-to-end models that we have.
Okay, good, thanks.
Thank you so much, Nikos.
Can I ask, I know we're running long, but can I ask a question?
Yeah, sure, go ahead.
So I understand we're in an intellectual paradigm shift or revolution, as you said, but the mean lifetime of any particular idea or state-of-the-art algorithm is a few months. And then we move on to the next thing. As an educator, I have to stand up in front of a class and try to explain to them what's fundamental and what's worth knowing, hopefully with a time constant of years. So I got to ask you, what should I say in my class? What's fundamental?
I think first of all, I think this is a great question. One fundamental thing, I think, and that has all actually survived the test of time, is the unification of language, unification of detection and grounding by utilizing the language input. The other thing, which was the theme of this talk, is that if you want your models to work on multiple tasks, maybe use language as an input early. You could do detection grounding as well as you could do instruction following. So I think that is the other thing. In the robot project, for me at least, one thing that I keep from it is that abstraction can help with some asterisks. So here we were abstracting into detection, concept generation, and execution. And I think this is really helpful for robotics because we do not have a lot of data to learn end to end. And in this case, it makes sense to learn perception from somewhere, learn how to do tasks, let's say from somewhere, maybe passive videos or something like that, and then only train our execution policies to do some low-level tasks. But in detection and grounding literature, this is not a problem because first of all, we have a lot of data there. And secondly, the language input early helps detecting the objects, which is like, for example, small objects and large objects. So I think in summary, one, unified detection and grounding, maybe use language for multiple tasks and do abstractions and do like abstractions wherever you think it can help and you have less amount of data.
I think that's a really interesting comment. It is deeply ironic that you say language is used for grounding because in the old days of robotics, we always thought language is the last thing you possibly want to use for grounding because, you know, seeing things, recognizing objects, doing things, you know, that had real meaning in the physical world. And words obviously are these ephemeral constructions. And so maybe this is an example of, once again, for computers, chess is easy and simple things are hard. And language is useful for grounding. And how my dog grounds things is irrelevant to AI.
I think the problem there is, let's say if we want to just detect objects like what maybe our dog does, then I'm perfectly fine with the current paradigm. You just have a bunch of images and you label all the boxes without any labels and so on. And you train on all the data that you have and it would work fine. The problem comes that when we also have to recognize objects, which humans do and they use for various other downstream tasks. In that case, the problem is that you have to define those concepts, which is pretty painful. So in that sense, you just use natural language and you have a lot of labeled data available and you train the model. So I think that's why the language grounding is useful here, but it's probably not accurate to conclude that perception needed this grounding. It's just that a task had this thing that we want to recognize the objects as well as chair, dogs, chair, things, and so on. We just want to say that, okay, these are the objects. Maybe they do this functionality, then it's fine.
Are there things a dog can't do?
Yes. So I think the question your question is that, do we really need these object classes, let's say, for doing interesting tasks? I think the main problem is that these robots have to interact with us humans, not only among the robots. So the only good, probably the easiest way to communicate between us is language instruction. So if I want my robot to do something, I would probably need to instruct it, instead of, like, for example, we have Roomba, which does not have a language and can do one task. But if I have a general robot, then I would need to instruct it to do a particular task, and I only have a language as a way to communicate. So I think language becomes a necessity because we have to interact with humans. And because it is a necessity, we need to have these objects labeled as orange and these things like that. So it's mainly because we want them to function. It's not because it would lead to some intelligence or something like that, probably.
Okay, thanks very much.
Thank you so much, Chris.
Have a fun time with your committee.
Yeah. I think they're kicking me out right now.